Okay, so welcome everyone after the break. And if you're watching this video on YouTube or on MSNY website, then I just wanted to say that Emily answered the question of Reed earlier when we were not recording. So if you want to know the answer, you have to ask Emily. And that's okay. Unless Emily wants to say something now. Oh, probably not. Okay, so without further ado, I'll just introduce the speaker. So Daniel Shapiro, part two of his talk, and now he's going to talk about cubes as test categories.
Thank you again, Chris. I've tried to remedy the pen situation, but hopefully it will. We'll see. Am I able to draw? No, I'm not. Okay, whatever. So yeah. So, right, today I'm going to talk about how the various cube categories we've considered are various forms of test categories. And I'm also going to tell you what that means. So classically, we use simplicial and cubical sets to give a convenient combinatorial model for spaces when we're doing homotopy theory. And by the homotopy hypothesis, whether you believe it as a theorem or definition, that means that these particular kinds, these combinatorial diagrams, simplicial and cubical sets, are a way of describing spaces or infinity groupoids. These also admit a description of infinity groupoids, and you can analyze how good or bad they describe infinity groupoids, but the fact that these categories are able to do so makes them very interesting. Now, so for several reasons, simplicial sets have been more common. And to me, it seems like that is primarily because their products work nicer, that the product of two simplicial sets gives you actually the product of their homotopy types. And we also have a particularly nice nerve functor from categories to simplicial sets. All other suggestions as to why simplicial sets are better than cubical sets are very welcome. But I think these are some of the most compelling ones. Though, of course, a lot of people just prefer simplices. But we can talk concretely about, from this perspective of the different properties a type of diagram might have, how well does it do? Like, we know that simplicial sets, cubical sets, theta sets, omega sets, semi-simplicial sets, other kinds of cubical sets, they all model spaces in some way or another, where we get, in general, we get a lot of different kinds of categories like these when we're studying compositional structures. In particular, that's where theta and omega come from in higher categories and multi-categories. So it would be nice to have a way of talking about how capable these categories of cells, I'll call them, how capable they are of describing the homotopy theory of spaces, or if you prefer, the theory of infinity groupoids. And so Grothendieck came up with this notion of test category with various addenda to describe when Presheaves over a category A is able to model the homotopy theory of spaces. And so the point of this talk will be to analyze when and how different cube categories are able to do this. And I think, actually, before I move on, I've had a lot of conversations with people where they say, well, simplicial sets have all of these nice properties, And why would we need to work in anything else? And oftentimes that makes a lot of sense. Something's been done in simplicial sets. You might as well work there. Except in a lot of cases, especially ones involving higher category theory and evidently type theory, it's much more natural to work with cell shapes that better fit the situation. And so if the properties that make simplicial sets convenient could be replicated in different kinds of diagram categories, like free sheets over different kinds of A, that is especially helpful. I think so. Anyway, I'll start by giving some background on test categories. I'm mostly following how Grothendieck developed this in pursuing stacks, albeit much abridged. But this is also going to follow papers by Maltsiniadis, Buchholz and Morehouse, and I also got a proof from Jardine's categorical homotopy theory, and a lot of this stuff goes back to Szyszynski as well. So we're going to define a functor we're going to define what it means for a functor to be a weak equivalence in categories. Because while we ultimately want to compare these diagram categories to spaces, coming up with a geometric realization functor from an arbitrary one of these is difficult to do in general without going through categories. So instead, we'll just work in cat and say that if the nerve of a functor f, from the nerve of C to the nerve of D, is a weak equivalence of simplicial sets, then we will say that the functor f is a weak equivalence of categories. And this is a much weaker notion than equivalence of categories. In particular, we know that if you have a natural transformation between two functors, that induces a homotopy between them, because that's true at the level of their nerves. So already we have that, any adjunction between two functors, adjunctions are now going to behave like homotopy equivalences because natural transformations are inverted in this homotopy theory, is how I like to think of it. So what that means is, because we don't care so much about the direction of our homotopies, we can say that a functor is a weak equivalence, an endo functor is a weak equivalence if it has a zigzag of natural transformations to the identity. Because in simplicial sets, this is just going to be a zigzag of homotopies, and when you realize the spaces, it becomes an honest homotopy. So this gives us a powerful tool. And we're also going to talk about when categories are contractible, which is when the unique map to the terminal category is a weak equivalence. And one of the most interesting cases here is going to be when our category C has a terminal object. Because if it has a terminal object, then it has a natural transformation to the constant functor at that term from C to itself, or sending everything to that terminal object. And that makes this map to the terminal category a homotopy equivalence. And I'm not sure if we'll get to using this, but a fun fact, if not something we'll use later, is by Quillen's theorem A, if we have a functor such that all of the comma categories, so the category of maps from something in the image of F to D, if all of those are contractible, where we can think of these like fibers of F, then F is a weak equivalence. And lastly, the reason we care about the homotopy theory of categories right now is because it actually turns out to be equivalent to spaces. Thomason put a model structure on categories that is quillen equivalent to spaces. While I'm not going to talk about model structures today, this means that we only really need to compare the categories A hat to cat. We only need to compare their homotopy theories to that of cat. So we can, for the time being, cut spaces out entirely, which will be convenient. So moving on from there, how do we define homotopy theory in one of these pre-sheaf categories? So first of all, we're going to start by comparing it to cat. So any A has a functor to cat that just sends an object, little a, to the over category, A over A. And we can extend from this to the functor from A hat to cat that sends a diagram X to its category of elements. And this is a left-con extension where each pre-sheaf in A hat is a colimit, and you can take the corresponding colimit of these categories, A over A, and that agrees with the category of elements. So we always have a way of going from A hat to cat. And what we're going to be interested in is, can we use that to define a homotopy theory on A hat? And just to give a quick example, if A is the semicube category, I think this is the only time I'll use it here, so I guess you need not worry. And we take the 2 cube as our pre-sheaf, then its category of elements looks like this, where the dots are the different cells, corners being vertices, the middle ones here being edges, the center one being cube, and the arrows are face inclusions among those cells. And this category has a terminal object, this one in the middle, and is precisely the over category into the 2 cube. So all of these categories A over A are going to be contractible in the homotopy theory of spaces, which will be important. So we want to have a homotopy theory in A hat, and while all of this can be done at the level of model structures, which was done by Sosinski, I'm not going to get into those details for the sake of time. So all we're going to be looking at is weak equivalences. And we're going to define the weak equivalences between 2 pre-sheaves X and Y as maps such that when you apply the category of elements, you get a weak equivalence between these categories. And likewise, X is going to be called contractible if the category of elements of X is contractible. Though note that that's different from saying that the map from X to the terminal A set is contractible. I'll get to that more. So, like I mentioned before, all representable pre-sheaves in A hat are contractible because their categories of elements have a terminal object. Now, for the terminal pre-sheaf in A hat, its category of elements is going to be the category A because it has one element in each component and all of the maps in A. So if the terminal pre-sheaf in A hat is contractible, that means that the category A is contractible in cat. So that's going to be a condition that we end up imposing in order for A hat to model spaces the way that we want, because we're going to want the terminal object to be contractible. Now, we also get a functor going the other way. So we can take a category C and send it to the pre-sheaf over A, given by, for each A, you take the set of functors from A over A to C. And so it's good to have maps going in both directions. And if I were doing this in terms of model categories, I would say we want to make those maps into equivalent equivalents. So this is how we compare the category of pre-sheaves over A and cat. So what is a test category? So Grothendieck called A weak test category if when you go from category, you take a category C, you apply this I star A, get an A set given by this, and then go back to categories by the category of elements. The co-unit of this adjunction goes from there to C, and A is going to be a weak test category if that is a weak equivalence. And what you can see is that at the very least from this, it's clear that this shows that A hat hits all homotopy types, because if we want these two things to be equivalent, and equivalent equivalence gives a somewhat more sophisticated notion, but what Grothendieck considered was just comparing the different classes of weak equivalences. And I apologize again that I can't write more of this down because of my pen. But what we want to have is that the weak equivalences in cat and in A hat correspond precisely, as do the weak equivalence classes. And so if for every category C, we can find something in A hat, namely I star A C, which is sent by L to the same homotopy type as C, namely this is a weak equivalence, that means that all of the homotopy types in cat can be realized by a pre-sheaf in A hat, an example being I star A C. So that gives us a sense in which the homotopy theories of A and cat are the same. Now, furthermore, I would have to go to the homotopy category and show full faithfulness of yada, yada, yada. But this hopefully,
Brandon,
yeah.
So are you saying that for a weak test category, the homotopy category is equivalent to spaces?
Yes.
To the homotopy category spaces?
Sorry, I should have said that directly. Thank you.
Okay.
Yeah.
So you don't need actually a test category for that. You just need a weak test category?
Yeah.
Okay.
The problem is you don't get as nice characterizations. So what we'll see is that when you impose some stronger properties on A, in addition to being a weak test category, it becomes easier to describe without checking all of these weak equivalences that A is in fact a test category or whatever other version of it. The other properties we get are nice, and I'll say what they are in a second, but yes, being a weak test category is sufficient to having the homotopy category of A hat, where you formally invert all of the weak equivalences, be equivalent to the homotopy category of spaces. So what are these other kinds of test categories? So we say A is a test category if A is contractible, so the terminal A set is contractible in A hat, and if each over category is also a weak test category. And this local property, so Grothendieck, if you ignore the first condition, that A is contractible, this property is called being a local test category. And you get some slightly stronger characterizations of like what that means in terms of the homotopy categories. I wasn't able to find a really nice description of what you get from being a test category compared to a weak test category, aside from that your functor from A hat to the homotopy category preserves the terminal object. But there are it's much easier to show that A is a test category or at least there are tricks that if you satisfy that property, you are a test category, not just a weak test category. And we'll see one of them. And having this local property is also convenient. But I admit something I'm sort of soul searching for is why test categories are so much better than weak ones, aside from the sort of clear practical advantages of the examples. And then our strongest notion is that A is a strict test category if that functor preserves products. So here it's very clear that we're getting something where we can use products nicely, which we do all the time and is very convenient. As I think I mentioned before, one of the nice properties of the simplex category is that products of simplicial sets agree with the products of their homotopy types. And indeed, delta is a straight test category. And for an example of a weak test category, we have the semi-simplex category. And we'll see by the end, hopefully, several examples of test categories which are not strict ones. So one of the tricks I mentioned for proving something is a test category is using intervals. So it makes a lot of sense to talk about intervals in homotopy theory because, again, it's something we use all the time. And here, what I mean by interval, in particular a separated interval, is a diagram like this, where we have an object I in A hat. So I is some presheaf over A. It has two maps from the terminal presheaf, and it's separated when this map is a pullback. So when these two maps into I are disjoint from each other. And my favorite example is that in our cube categories, or most of them, that the 1 cube is a separated interval. So if we have degeneracies in our cube category, then the 0 cube is terminal. And so we can then just define this interval by the source and target inclusions of the 0 cube into the 1 cube, and those are disjoint from each other in the appropriate sense. And so this gives a separated interval. However, if our cube category has reversals, then they're actually no longer disjoint because you can swap them with the structure map of cubical sets. And so then instead we use this cubical set. So the reversals just swap these two pairs of opposing arrows, and we have two different elements which are separated, whereas these two would not be considered separated. So intervals are nice, and they behave kind of like what we expect, though so far they've been defined very generally. And oftentimes we're going to want to impose extra conditions on that interval. And the first reason that I bring them up is because strict test categories can be described as categories A where presheaves over A have a separated interval and A cross B is contractible. Now, A doesn't necessarily have to have products, but you can take the product of representables in the presheaf category A hat. And as we see in the simplex category, the product of two simplices is a contractible simplicial set. So that's the property that we want, in addition to just the existence of a separated interval. We're not really going to use it very much, at least in this characterization. So now we have enough background to show that some of our cube categories are strict test categories. In particular, if we have degeneracies, symmetries, and diagonals, so that the cube category is Cartesian. It actually has Cartesian products.
So we have a question, if I may interrupt you. So I'll read it, maybe. I'm a bit confused by the condition that each over category be a weak test category in the definition of a test category. Since we have a terminal object looking at A over star, we'll say that, okay, wait, sorry. I'm not very good at reading. So, can you see the question? And I'll read it again. Unless Morgan can say something, if she's here.
I can try and ask. Just my Wi-Fi is a bit spotty,
yeah.
so I thought, yeah.
Yeah.
Go for it. Unless we're experiencing spotty Wi-Fi right now. Okay. See. Okay. Let me try to read it again. I'm a bit confused by the condition that each over category be a weak test category in the definition of a test category. Since we have a terminal object star looking at A over star, we'll say that A also is a weak test category, but it seems like requiring slices over all other objects to be weak test categories is a lot. Does anyone have any comments about this? Or maybe it will be clear as we go along.
So it's definitely a strong condition. So let me see. Each over category has a terminal object. So being contractible is easy. I don't think I included that in the definition of a weak test category, but I believe that is implied when C is the terminal category. So it will certainly be contractible. It's a much stronger condition. I hope this is answering the question. In practice, a lot of the categories that we work with have this property. You can see, for instance, that the semi-simplex category does not have this property because all of the maps point in the same direction, and the over category at the zero simplex is just the terminal category, which is definitely not a test category because sets don't model homotopy types. I hope that gives some answer, but I'm happy to revisit this when.
Well, I think that gives an answer. Morgan says, okay, thanks, it's very helpful. So, okay. Yeah, I think it's good of a comment that an answer can get.
Yeah, and honestly, like part of why I wanted to give this talk was to learn more about test categories, and the motivation for the definition of test category is still something that I'm working through internally. So yeah, I think that's a good question, if I understand it correctly. So I was saying that any Cartesian cube category is a strict test category. Yes, and this proof is very short because we know that it has a separated interval because I just told you what the interval is. And it has Cartesian products. So the product of representables is also representable, and all representables are contractible. So right off the bat, we have a bunch of strict test categories arising from cubes. Now, I want to do something a little bit stronger though. So when Grothendieck originally wrote about test categories and pursuing stacks, his motivating examples were the simplex category and the cube category. And while he did some proving for the simplex category, he didn't as much for the cube category. And it was later observed that the traditional cube category, which I would write as box del sigma so you have degeneracies but no connections or any other fancy business, is a test category, which I will hopefully convince you of forthwith, but not a strict test category. Whereas when you have connections, even just one type, in the written plus or minus here, where I think I meant to change to 0 or 1, so I hope you'll forget that. Then if you have either connection, we actually have that it's a strict test category. And I'm gonna walk you through a proof of that. So first of all, so we're using the same theorem. We need a separated interval, certainly has that, and we need the product of representables to be contractible. So that's what we're gonna focus on. And the way we're going to do that is step by step. So if we have a product of representables, m cubed cross the n cubed, we want to go, if we can show that that is weakly equivalent to the m cubed, which is contractible, then we're good to go. And we can break up that map into identity cross a degeneracy on the second component at each level, to reduce the complexity of this. And so if I can show that all of these maps, identity cross sigma 1, are weak equivalences, then we're done. And the way we do that is, well, a weak equivalence in A hat is something sent by the category of elements to a weak equivalence in cat. And here I wrote homotopy equivalence because that is how I'm going to go about proving it. So what I mean by that, I'm going to tell you what a homotopy inverse is. So if we take the identity cross sigma 1, that has a section, namely identity cross del 1, 1, where I omitted the top index. So it has to be more general, but that should be clear from context. Here it's n plus 1. So those are, of course, those compose to the identity on box M cross box N, which I hope I've already written down. Yes, because I can't write new things apparently. And compose to, but they don't compose to the identity on category of elements of the m cubed cross the n plus 1 cube. So we're going to try to find a homotopy from that composition to the identity. And if this mess of maps and indices is confusing, I believe there's a more geometric picture coming up. So first of all, what does this category look like? It's the category of elements of the m cubed cross the n plus 1 cube. So an object in either of these representables is a map from some cube, say q, to the m cube, and then likewise from the same q to the n plus 1 cube. This is an element of this product presheaf, and therefore an object in the category of elements. And the morphisms just correspond to precomposing these F and G with maps in our cube category. So what we're going to do then is define an endo functor on this category of elements. So for F, so we take any F and G of this form, and for F, we're going to say replace it with something from the q plus 1 cube, where we just project away the first component to q-dimensional cube, and then go to the m cube via F, and then G is going to get a little bit more complicated. This is where we're using the connection. So, excuse me. What we're going to do with G is, again, we're going from the q plus 1 cube, but instead of precomposing with a degeneracy like we did for F, we're gonna tensor our original map G with the identity. So now we're going to the n+2 cube, as opposed to the n+1 cube, where the first component is just the identity. So we've just added in an extra dimension in both the domain and codomain and not done anything with it. And then we do something with it by applying one of these connection maps, which is going to look like this. So I've drawn the first dimension horizontally. So this is the dimension that we've added, which was acted on by the identity in this first map. And going vertically, we have the rest, the n+1. And what this degeneracy does, rather this connection map does, is it says, and maybe this picture is not an entirely perfect description. No, this seems good. So this map sends on the left. So the left copy, the source copy of delta n+1 goes to delta n+1, which is this arrow. I should probably have written it. And then on the other side, the target copy of delta n+1 is sent to what looks like the point, but what is actually going to correspond to where we want this homotopy to go. So this picture will hopefully be more helpful in that what F does, what PF does, is it just sends F, which is a cube in the M cube, to a higher dimensional cube, which is degenerate on. And what PG is it takes G and it sends it to a cube, which adds an extra dimension. At the beginning looks like G, and then serves as a homotopy in the sense of just having an abstract cube from G to the map given by composing this face and degeneracy map. So what we've done here is we've replaced the last component of G with a 1. And I apologize again that I cannot write more of this down. But the idea is that G sends Q somehow to each component of delta n+1. And what we've done is we've replaced that first component with a 1 on this side. And the reason we want to do that, and why I called it a homotopy, is that we actually have a natural transformations from both of the functors we're interested in on this category to P, given by the structure maps. So F and G include as the source face of each of these two cubes, and F and del11 sigma 1G include as the target face in this dimension of these two cubes. And these are, because these blue maps are actual maps in this category of elements, these amount to natural transformations. And so because of that, we have a zigzag of natural transformations from the identity to P and from this functor to P. So that gives us the homotopy we need. And the information to extract from all of this is that connections make it easier to define homotopies from representable cubes. That we can go from the identity to something closer to being a constant. And therefore, any cube category with either type of degeneracy is a strict test category. And if we use the other kind of degeneracy, then you would just reverse this picture and reverse the order of these, or just reverse these two face maps when we're doing the natural transformations. So that's very exciting. That means that any kind of cube category with connections is just as good as the simplex category to do homotopy theory if you want to model spaces and model products. which is pretty good. But how do we deal with...
Ezra asked degeneracy, you meant connection?
Yes, I did. Any cube category with degeneracies and connection, and a connection. So it can be either the soup or the inf version of it, is a strict test category by this argument. Thank you. But this doesn't work when we don't have a connection. It uses the connection very explicitly. So if we want to look at the other cube categories, we're going to need to get a little bit more creative. And in particular, we want to have a nerve from categories to A sets that might be nicer than the one given by the over categories. So you can use any functor for this. And Groth and Dieck determined some properties on such a functor that lets it suffice to describe being a test category. So I'm going to write 2 for the walking morphism category, and we're going to use this theorem that if we have a contractible category A and a functor I from A to cat, then if I of A has a terminal object for all A, which was true for I sub A, which picked out the over categories, and if I star of the walking morphism is not just contractible, but if its product with representables is contractible, then A is a test category. And the idea here is that I star of the walking morphism is going to be our interval. Something that you notice is not part of this theorem, and it was before. And what we're showing is that this interval isn't just contractible, but has the extra property that it's contractible when you take its product with representables. So hopefully it will be easy to see parallels between this proof and the previous one. So first of all, we're going to show that all of our remaining cube categories are test categories, even if we don't have connections. Though I meant to say with degeneracies, that's important. Semi-cube category is not a test category. So we're going to define a functor from our cube category into cat that sends the 1 cube to the walking arrow, which is how we tend to think of it, and the n cube to the n-fold product of the walking arrow. And if there are reversals, we don't want to do that, as for the reasons I mentioned before, and then we're going to use this category instead with 2 arrows. And both of these categories have terminal objects, as do all of their products, so we're good on that front. And what we need to prove is this last bullet point, that products with representables are contractible. And just like before, we do that via a homotopy equivalence between categories of elements. So we're going to go from the category of elements for the n cube cross our, what I'll call our interval, to just the category of elements for the n cube.
Reed asks, does A is a test category here still refer to the canonical functor I sub A to cat? So here you consider a different I.
Yes. So yes, thank you for mentioning that. So I didn't get into it, but the idea is that if we have any functor with these properties, then you can prove the same thing for the canonical one that we used before. So the definition of test category is still uses the canonical one, but you can show that this is equivalent.
I see, yeah.
So
I see, I'm sure the device Reed also sees, but yeah. I guess, yeah. I guess, so would would simplicial sets be a good example of that? Where
Yeah, so with simplicial, so, okay. Oh, I really wish I could write more things down now. But,
because the I sub delta is different from the canonical inclusion of delta into
yeah.
categories, right?
So
we
the
could
reason,
technically work with this, like the canonical inclusion, and then just sorry.
yeah, absolutely. So, like you were saying, simplicial sets are a great example of this because I sub A or I sub delta is not the usual inclusion from the simplex category into cat. And part of the motivation for using these different functors, which are when they have the appropriate properties called weak test functors, is so that we can replace I sub A with a different I that's more convenient. But what's important to note is that we only do it for I star. So we only use this to go from cat to A hat. We don't replace the category of elements, which is defined using I sub A, because that's not always going to work. But what we know is, in the case of simplicial sets, for instance, if you use the nerve functor, the usual nerve functor from categories of simplicial sets, that's going to work. So that and this functor we're using for cubes, which is how cubical nerves are defined for people who use those. That's why we work with a more arbitrary choice of I. So I hope that answers the question.
I think yes, I think it does answer both questions.
Awesome. So we want to basically repeat the argument we did before. Now, before we did it in steps where we only did one dimension at a time because it's easier to see that way. You're only using one connection. Here, we don't actually need that. So we're going to do the whole thing at once. And again, we're going to look at what are the objects in this category of elements. So the first component looks the same. It's just maps F from the Q cube to the N cube, which I think before was M, but hopefully that's not confusing. Except now, instead of a cube in the second component of our product, we have I star, we have the interval, which we've defined using the walking morphism. And so now, the second component of each of these elements is a functor of categories from the qth power of 2 to the walking arrow. And in particular, we're no longer bound by the restricted structure maps of the cube category. We actually have all functors at our disposal, which is the relevant point. So we have a homotopy inverse, which goes from this over category back to the category of elements, where if you have a map F from Q to N in the over category, that gives us F and the constant functor from 2 to the Q to 2, and it's constant at 1. So it sends everything to the target. And this applies just as well to any category with a terminal object. And you can check that this is functorial. So if you compose these from here to the left and then back, you just get the identity because F goes to F const, goes back to F. So we need a homotopy in the other direction on this category. And we get that using exactly the same kind of argument, where so we do the same thing on the left, in the left component, where we just precompose with a degeneracy. And on the right, we also take 2 to the Q plus 1 And we send it if the first component is 0 to g of x, just as before. And if the first component is 1, then that side of this hypercube looks like the constant map. And so we get the same kind of picture as before, where we can define this homotopy, so to speak, from G to a constant. Before it was only constant in one dimension, but now we can be a bit more forward. And the reason we can do this, even though our cube category doesn't have any connections, is because we're working, when we use I star, we have the full subcategory of these products at our disposal. So we get all of the maps in cat, and we can use them in constructing this homotopy. And then, as before, f and g include on the left in these cubes, and f and const include on the right. Those are natural transformations, and therefore we get the homotopy we need to show that this map is the weak equivalence, therefore this is contractible. And so all of our cubes are test categories. Now, originally, so that shows that everything's a test category. Originally, I was going to draw some pictures showing why these remaining cube categories are not strict test categories, but I don't seem able to actually draw as I expected. So I'm just going to tell you that the cube categories that are left, namely those which are not Cartesian and don't contain any connections, aren't strict test categories. And you can prove this by taking the product of the one cube with itself and just working out what its homotopy type is. In each of these cases, it ends up being a wedge product of some copies of S1 and S2. And it's definitely not contractible. And I can send a link to a paper that has those pictures if people are interested. The conclusion is that of
what paper is that?
So I saw those pictures first in Buchholz. Oh, I'm gonna butcher these names. I'm sorry. Buchholz Morehouse.
Buchholz Morehouse.
Yeah, but I think they may also be in Malziniadis' paper. So I am hesitant to assign credit before checking. Yeah, they include pictures that show what the product of the one cube with itself looks like, which makes it pretty clear that it's not contractible. And the conclusion here is that all cube categories are test categories. So all of them are, except with generacies, which I apologize for not writing in. All of these are capable of modeling spaces and therefore infinity groupoids. But if you want the model to be particularly nice, then you'll want to use either a cube category with Cartesian products or with degeneracies and connections, or a connection. And I think I'll stop there.
All right, well, thank you very much. So let's have a round of applause. So if you have your camera on, like we're applauding one way or another. Okay. And yeah, please ask questions, unmute your microphone and ask a question, or write it in chat. And despite my limited ability to read in general, I'll try to read it, and we'll see what's going to happen.
It's very fair. Apparently, I can't write, so.
I'll maybe, okay, if no one, yeah.
I have a question.
Great.
It's not really a question either, but before you get in, for me, for the simplices, so there was a discussion earlier, why simplices? And one reason I think they're treasured is because of the join operation. So I'm just wondering if there's a replacement for that in cubicle land.
I'm glad you mentioned that. That's something that I've thought about thinking about, whatever that means, very recently. Yeah, I've kind of made it my mission to try to figure out why people like delta so much, and everybody has a different answer. So it's been kind of an exciting journey. And the reason I care is that I want to be able to say, like, if I can describe very simply a property of delta or a construction of delta that gives rise to all of those properties, then I'll feel very good about myself. And this one, I don't have a good answer to. Like, okay. I hope that, for instance, the existence of a nice canonical even nerve functor from categories is actually sufficient to determine a lot of this stuff, including.
Okay.
But
well, somehow for me, the key spot where join appears is sort of internally in Quillen's theorem A. I could put it that way. So if you are putting Quillen's theorem A in as a axiom, that might be the answer. I don't know. Is Quillen's theorem A an axiom in this story?
It is definitely used. So I sort of glossed over all of the places where theorem A gets used, and I put it in the notes, largely because when I wrote it, had not yet figured out how much I was going to do that. But at least in Grothendieck's presentation, which is mostly what I read to prepare this, that gets used a lot in reducing the conditions. So like in weak test categories, for instance, you only need to check this map as a weak equivalence when C has a terminal object, and that follows immediately almost.
But I see. But so it's being used over in the category side and proved, let's say, using join with simplices or décalage or something. And then,
yes.
But there's a kind of, there may be, just as there's a simplicial generalization of Quillen's theorem A, which includes the category theory version by the fact that the simplicial category is a test category, but obviously in some sense there's more. So I wonder if transporting Quillen's theorem A over to the cubical side would be the appropriate way to replace the join.
That's a really interesting point, and something I may want to think about. Because my outlook on these things tends to be that the most fundamental descriptions of these things come from nerve functors, and categories have a canonical nerve functor to simplicial sets constructed in a particular way. And that, by what you just said, would, if you have theorem A in categories, give you the join through the transporting of theorem A to simplicial sets. And so other categories which arise from a similar construction may have the same thing. And maybe that perhaps, and again, back to rank conjecturing, test categories could be phrased from that perspective as categories that admit a nerve functor, like the I that I wrote down before, which preserves all of the important structure on cat, even when it's not going to simplicial sets, which is in a sense the canonical choice.
Can I offer maybe a slightly different direction in which this question could be taken? So maybe what you're asking is not really about the join, but maybe about counts. So maybe that points to something else. So what are simplicial sets? Or what is the simplex category? Right? You would start with the interval because you want the interval to do homotopy theory, and then you would start taking counts on it, and that would produce simplices.
Right. Mm-hmm.
Now, what is a cube? Well, you would start with the interval, and you would start taking products of it.
I see. Yeah.
So, in some sense, join is fundamental to simplicial sets the same way the geometric product would be fundamental to cubical sets.
I see.
So that could be one way of seeing it. But then there's still a question of how do you approximate between the two shapes, and maybe I'll advertise a talk that's gonna happen next week. So there is an analog of this Royal model structure for cubical sets, and at some point you need to compare the two. And so Brandon Doherty has this very nice theory of cones in cubical sets that kind of lets you approximate between the two shapes. So between something simplicial and cubical, and that's the main tool used to compare the Royal and the cubical Royal model structures. So I'll just advertise the talk, and
yes, I'll stay tuned. Yes, definitely. Okay. Okay. Thanks.
Okay. Any other comments? Questions?
Yeah, I guess I have a question about the sort of, if we're using some kind of cubical sets to model spaces, will we have another way to find the homotopy type of a cubical set already, which is through this like geometric realization functor to top, for example? And it doesn't seem like it fits very conveniently into any kind of triangle involving cat and top and cubical set. So what's the easiest way to see that the triangle commutes up to, equivalence or whatever?
Yeah, so the way I think of it is that so first of all, if you take, let's see,
because otherwise you draw a bunch of these pictures and you think you've like shown that, you've computed that something is S1 wedge S2 or whatever, but actually you were supposed to do some computation involving the category of elements of something, and it's a completely different computation a priori.
Right. So if you take this functor I, and I see what you're saying, because we use the category of elements. So
the push out in categories is not going to compare to the push out of spaces, for example, when you take the Nervo,
right,
which is what you want to do, I think.
So I think typically, so the category of elements are all contractible, and they include into each other, it is a functor.
Right.
So like A over A, this is a functor from, A over A is always contractible, and functorial over, say, the cube category. So the idea with the category of elements is it's sort of a not very efficient, but always exists way of determining what space, or what diagram of spaces, more accurately, the objects of A are meant to look like. And in the case of cubes, I don't think I have, actually, there's a picture. Let's see if I can find it. In the case of cubes, what you get here, while yes, it's not like, I guess what I'm saying is this geometrically realizes to a square, right? You have composites along these diagonals from each corner to the center, and in the simplicial and in the nerve, the simplicial set, which is where we get the realization from cat to spaces. So we go from cat to simplicial sets, geometric realization to spaces. This is actually going to be a cube, or a square. And in general, it's going to be a cube. It's just going to be generated by more maps. So I think that's sort of supposed to be the idea. It's not the most efficient way of getting that square in simplicial sets, for instance.
Sure.
But isn't there a general answer to the functor that we use to show that the cube category is a test category is a test functor, right? And I think isn't it in general the case that if you have any test functor, it's weakly equivalent to the canonical test functor given by a category of elements?
I think so.
So that gives like so even though you're using a different functor, it is weakly equivalent for general reasons.
Yeah. So the only reason I hesitate is because I somewhere in the literature, I saw a very specific warning to be careful not to replace the category of elements functor, even when you're using a weak test functor. But I think that is,
yeah. In the Thomason
sorry,
in the Thomason model category, you have to subdivide first, right, before you.
Yeah, like I think it has something to do with that,
yeah.
And it like, I think when you're proving something as a test category, it is important not to replace category of elements with some other functor to cat. But, well, the functor from cat you can replace. But I think when you're doing the realization, it shouldn't matter.
So the sort of argument that I was thinking along the lines of would be something like, for showing that the geometric realization at top computes the right homotopy type would be something like, well, it's determined by this co-cubical topological space, which is sort of the, right, it sends cube n to the topological n cube. And then you check that this diagram is really cofibrant or something. And so and that each object is contractible. And so that should imply that it computes the right space, because the idea is that each representable was supposed to be contractible. But I feel like I'm using more machinery there. I mean, I guess maybe I had to have that machinery in place to even define this geometric realizations. Maybe that's a little bit unfair.
I think in practice, a lot of the test categories that we use are really categories.
Yeah.
And while it's certainly not clear that there's any implication there, and there probably isn't, like, that's pretty good, I guess I would say.
Okay, thanks.
Any other questions or comments? Maybe I'll ask a very open-ended question. So test categories are supposed to tell you when some category of shapes is good enough to model spaces. Can you envision a similar theory for infinity one categories?
I'm very glad you asked that. That is one of my ongoing research interests that I have zero progress to report. But this is something that, this is a large part of why I was interested in giving this talk, because something I think would be really cool is because we know that there are lots of different kinds of categories which admit descriptions of different sorts of higher categories. Like there's, delta works for infinity one via quasi-categories. Delta cross delta works for infinity one via complete Siegel spaces. You have, what else? Marked simplicial sets can be realized as appreciatives over a certain marked simplex category. And in general, for infinity n categories, delta to the n, theta n cross delta, marked simplicial, the marked simplex category, like there are all of these different options of categories whose preciates admit these homotopical models for infinity n categories. And I would just love for there to be a similar notion to what we have for test categories, where you say, okay, this is like an n test category. It hosts a model for all of these different more algebraic structures. And something like theta would probably be all of them, because it hosts infinity n, where n can go up to infinity. And I'm very curious, one, if this is a thing, how it would be defined, and if so, where do cubes fit into the picture? Because it seems like from what some of the talks next week are going to cover, it's cubes are hopefully a one test category, or at least some of them. But cubes are strange. They have higher dimensions, right? So like, it's certainly feasible to think that they might be able to describe even higher dimensional compositional structures. And so something I am very interested in going forward is, what would that look like?
No. Okay. Yeah, so again, I think Yeah, next week we have talks that are supposed to cover. I think this week is themed as cubical sets as infinity groupoids. Next week we're moving to infinity 1 and infinity n, and then third week we are going beyond that. So now, yeah, any other questions or comments? I think we are like way over time.
Oh yeah, wow.
So, but yeah, I think it's a good conversation. So if there are any other questions, please ask them now, and otherwise I'll stop the recording. Okay. Well, there's one more question. Oh yeah, the question is, would you be comfortable sharing your slides? But
yes, I'll want to edit them a little bit, just maybe to add in references and correct some mistakes I found, but absolutely.
Yeah, like those anti-Semitic jokes especially would be good.
Those what? Sorry.
No, nothing. I just said it would be good to remove the anti-Semitic jokes. But, no. Okay.
Well, that's on the video end, which I'm probably fine with sharing as well.
Okay. Okay. In that case, I have one suggestion. Let's thank Brandon again. He spoke for over 2 hours, and he's not Fidel Castro, so it's quite an achievement.